It is a pleasure to welcome you to the fourth edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP Lecture Series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The Pan IIT Lecture Series on geotechnical engineering is consisting of 6 talks, which have been delivered by the pioneers in the field of geotechnical engineering from different IITs. The following lecture is the second talk of the session 3 of the lecture series. This lecture is on study on utilization of municipal solid waste, MSW Fines, for geotechnical purposes, which will be delivered by Dr. Supriya Mohanty. Dr. Supriya Mohanty is working as an assistant professor in the Department of Civil Engineering at Indian Institute of Technology, BHU, Varanasi, India. She received her PhD degree in civil engineering from Indian Institute of Technology, Kanpur, India, and her BTech degree in civil engineering from Veer Surendra Sai University of Technology, Billa, Odisha, India. Her fields of research interest are liquefaction potential evaluation, soil dynamics, geotechnical earthquake engineering, and waste utilization. She has produced over 66 publications in peer-reviewed journals and conferences. Her honors include the ISET Somsher Prakash Early Career Research Award by ISET, Roorkee, the Early Career Research Award by SERB, DST, Best Researcher Award by VDGOOD Professional Association, Young Scientist in Civil Engineering Award by Venus International Foundation. She has been received University Gold Medal, Achyutananda Pujari Memorial Gold Medal and University Silver Medal during her BTech. She is a life member, associate member and member of various professional associations such as American Society of Civil Engineers, Earthquake Engineering Research Institute, Institute of Engineers, India, Japan International Cooperation Agency, Indian Geotechnical Society, ISMG, ISSMGE, Indian Society of Earthquake Technology and Association of Consulting Civil Engineers, India.
So today I am going to discuss on this utilization of municipal solid waste, particularly MSW fine fractions for geotechnical applications. So first I would like to thank my PhD students. This work has been done by one of my PhD student, Parul Rawat. So she has considered Varanasi as the site location for this MSW waste collection. From the Varanasi dump site, she has collected the waste. So all the experimental and even whatever field work, limited work we have done, all she has done. So it is the, I think, outcome of her hard work. So mostly I will focus on the technical and geotechnical parameters, because our objective is how we can utilize this fine fractions of this MSW or municipal solid waste. Fine fraction means soil-like material mostly for various geotechnical, not only geotechnical, construction applications. So if you consider this municipal solid waste, so already Das sir has discussed means a lot related to coal ash, fly ash, and different type of bottom ash and all, and how to utilize it and what are the critical parameters. So I am going to discuss only the municipal solid waste, MSW waste, means source of generation, then how we can utilize it. If you see the past literature, fly ash and different type of coals, it has been used in construction, like cement and bricks, even filling lowering area and all. But this acceptable rate or acceptance of municipal solid waste fines, that is soil-like material, it has not yet been proved. So that's why we thought as this area has not been focused, so let us study. And in Varanasi, you know, the city location, and this is very small city, but population wise, and if you see the traffic and all, it is very difficult to manage the city traffic management. It's also a tough task. And this municipal solid waste, so management of this waste is difficult, particularly not Varanasi city, even throughout India. So I will discuss that slowly. So what I will say, this waste, whether it is municipal solid waste or industrial waste, this is our waste only. We are generating the waste, and it is our responsibility how to properly utilize it and keep our environment clean and sustainable. So we need to find the way, because we can't stop the generation of the waste. As the population increasing, our requirement and day-to-day life, we need means our whatever minimum things we need. But from that, obviously there will be waste generation. So we can make it zero. Other option is we have to think the different ways to utilize it. So in this study, what Parul has focused, if the soil-like material fine fraction can be utilized in various geotechnical, not only geotechnical construction activities, so it will at least contribute some percentage of this waste. So coming to outline, I will just brief to this problem, MSW, then landfill mining, then how to characterize it. And then I will come to our case study of Varanasi dump site and utilization of this soil-like waste, mostly fine fraction, and possibility for reuse or whether treatment is required or not. And this is the outlines. So coming to the introduction part, so MSW, I can say it is a problem not only for us, worldwide, all are treating this as a problem. So this municipal solid waste, sometimes urban solid waste also we treat this waste as. And mostly it contains household waste, or you can say domestic waste from our house. And additionally, it also contains like commercial waste, construction and demolition waste, and waste from hospital, institution, and means covering within a given area of a municipality. So this waste, so who are generating? We are only generating it. So we are calling this as a problem. So we need to find the solution, and the way means different possible way of utilizing it. So then if you see the waste composition of means worldwide, then here you can see 44% of the waste is biodegradable, and nearly 70%, this is world scenario, and nearly 70% paper or cardboard type material, particularly MSW, municipal solid waste only, not other waste. Then like plastic 12%, glass 5%, these are the composition, or you can say percentage. And coming to our Indian scenario, if you see, we are also having nearly 47.5% of biodegradable material, paper nearly 8%, then plastic, rubbers 9.2. But thing is, if you check the quality of the MSW, quality of waste worldwide and quality of waste here, so quality of the waste, it completely different, and it also depends on the living standard of the people, how we are means what we are utilizing, and what you are producing as a waste. So it depends on the I can say living standard, and also low income and high income group of people. So that's why quality of waste in Indian scenario and worldwide is different. So that's, and their application utilization and our application utilization will be different depending on the means whether hazardous material present is present or not. We need to check that, because all these wastes are means not only a specific household waste, it contains hospital waste, in means construction demolition waste, and also other waste and domestic waste. That's why first step we have to go for chemical analysis. I will address what are the minimum chemical test we should perform. Then this one is showing you this world waste production and GDP for top 20 countries. So here we have considered, so new the only top 20 country. If you see, we are standing at the third spot, and if you check the GDP and MSW means municipal solid waste production, so you can compare the GDP and the waste generation. So soon we are going to means cross US and China in the waste generation means production part. Why this is also clear, because of our population growth, and it is increasing exponentially. So as population is increasing, we can't stop the generation of the waste also, that also will increase. So this is the comparison only GDP and MSW means top 20 countries. Then problem here is, if you compare US and other country and India, so problem here is particularly for MSW is the management. We are means not able to manage the waste properly. So if you check this Planning Commission report of 2014, so there you can see nearly 471 millions, which is about 34.5% of the total population. They are residing in urban areas. Why? This is also clear, because all the metro city IT sectors and industries are in urban areas. So we all prefer to reside in urban centers, and they are generating nearly 62 million tons of MSW per annum currently. And it is projected that by 2023, these urban centers will generate nearly 165 million tons of waste annually, and by 2050, it could reach 36 million tons. So you can see this generation is directly proportional to this population and industrialization growth. So the area required from 2031 to 2050 would be 43,000 hectares of land, landfills, and piled in 20 meters height, 20-meter height of these landfills. Then if you compare the collection efficiency, so major metro cities, the efficiency is nearly 70 to 90%. But if you go to rural area or small cities, it is below 50%. Even I can say for Varanasi city, our campus also, we are trying to at least collect waste separately. But at the end, they are dumping it tractor, and they're taking it to the dump site. So very difficult to manage and collect the waste separately, segregation of the waste at the source, particularly our Indian scenario and small cities. So that is the problem, management thing. And we are not paying any attention to any scientific or safe disposal of the waste. All waste, even if you consider in our home, what we are doing, are we segregating the waste in separate packets, or we are putting in a common dustbin? So this we only have to think what we are doing. It means we have to start from one person only, means from our home we have to start, then it will grow slowly. And there are only 59 constructed landfill sites in India, and 376 are under planning and implementation stage, and 1305 are identified for future use as per Central Pollution Control Board 2013. If you check the CPCB report of 1920, here you can see nearly 1359 landfill sites are identified. You can check the number from 13 to 20, how it has been increased. And this is because of huge generation of the waste, and we need site to dump it. So, and 321 already constructed landfill sites, and this 376 under construction, and the 379 is operation. And if you check this figure 3151, this is the total number of existing. It means already we have MSW waste in this dump site, so 3,151. So our objective is, whatever the existing dump site is there and already waste is there, so can we reutilize that waste so that same dump site can be utilized further for in dumping the waste? So this thing means in our study we are trying to focusing. So existing dump site, whatever we have, try to utilize the collect the waste and utilize it in various construction or geotechnical application where bulk quantity of waste can be utilized, because you know the quantity of the waste we are generating daily. So if we can utilize bulk quantity of this waste, so bulk quantity means you need to think the project like highway construction, embankment construction, low-lying area, filling low-lying area, this type of where bulk quantity can be utilized. Then what could be the solution for this problem? First step is waste minimization. Means we can't stop the generation of the waste, we can minimize it. So minimize means from our source level, we try to minimize the waste, try to use less plastic, and recycling and reuse. That thing can be done, and benefit of waste minimization. Next is understanding the type of waste. Means if you see our Indian scenario, we are changing from agricultural waste nation to industrial and service oriented. That change can be seen. And past, if you see the past 20 to 30 year record. So now, and as we are changing from agricultural waste to industrial waste, So our day-to-day life, our living standard, and also requirement, and it means what you are using in day-to-day life, that also is changing in day-to-day life. So that your waste generation, it completely depends on your living standard, what you are using in your day-to-day life. So understanding the type of waste, so we have to focus. Now we are changing from agricultural waste to industrial. So not only the MSW, other type of waste also will generate. So we need to focus on that. Next is efficient waste management system. Means we need to manage the waste efficiently. How it will be possible? First step is, if you are collecting the waste, the collection also, it has to be done separately. And if you are you are generating the waste from your house level only, you need to segregate the, you try to segregate the waste, different type of waste. And if the similarly collection also can be done separately, so this will save the this segregation unit time. And we also need proper transportation system, monitoring, investment on infrastructure, technology, and active participation, public and government also, because people should accept this efficient waste management system. Particularly integrated solid waste management system. Public awareness also we need. And fourth is, we can also introduce new policies and technique through R&D, like by conducting research and activities. And we can also suggest, this material can be used for road or embankment construction, like tires. So for that, we need to prove our results, or whatever outcomes we are getting, we need to prove and justify that through R&D activity. So this part is completely I can say it is to this we can say PhD students, or faculty and R&D organization, they can do this part. But other things, it can be done at source level, like waste minimization and efficient waste management system. This part is our responsibility to suggest or possible new application and new techniques and scientific landfill technique through this R&D work. Landfill mining, coming to landfill mining is whatever the, if you check the previous slide, whatever the total, this means existing dump sites 3151, if from that existing dump site you are excavating and treating the waste from or active or inactive landfill for any of the following purpose, then it is treated as landfill mining. So that includes conservation of landfill space, reduction in landfill area, also eliminate the contamination of like groundwater table. And nowadays we are using this waste MSW for waste to energy generation. In our Varanasi also, we have one waste to energy plant. From that site also, we have collected some sample, how they are utilizing this MSW, particularly MSW only they are using for generating power. I will discuss that in coming slides. Then reuse of recovered material, reduction in waste management system cost also. This way we can reduce, and number of landfill site also can be reduced. Also site redevelopment for further use. So if you check the past study, so you can see there are many field study as well as lab studies are available on raw MSW, means whatever the MSW it is available in the site condition, same raw material, means raw or aged MSW. 10 years, 20 years aged MSW, many studies are available, field study as well as laboratory study. But if you consider the soil, only soil-like portion of this MSW, very limited studies are available. Only I can say IIT Delhi people, they are working, and also they have suggested for embankment application. Their result also I have compared. Then also landfill mining is a dispute area. So to suggest or recommend this material to be used for construction purposes, we need to validate and justify our result. So to use this fine portion of waste for geotechnical application is still less challenge because of its heterogeneity and complex chemical and geotechnical properties of the municipal challenges. Very few researchers have addressed this issue. So that's why in our study we have means considered this Varanasi dump site as our study area, and this shows the methodology. So what we have done, we have collected the sample from one site, means source MSW raw sample, that is the Ramana landfill site. I will show you the site location pictures. Then another site is Karsada plant. So this is a waste to energy plant. So this plant, they are only using MSW from the Varanasi dump sites to generate power. So it has been supported by NTPC. So what they are doing, they are using the waste for generating the power, and means 4 rejected sample, they used to dump it again. So only passing 4 they are utilizing it. So what means in our second part, what we are trying to do, we have collected sample from this plant also, whatever material they are rejecting it. So that we are trying to include as a fiber. So this part I will discuss at the end. So first step is this from this Varanasi dump site, Ramana site, we have collected the raw sample bags, and then air drying process was continued for 24 hours depending on the means weather condition, and then this screening of this dried MSW waste, not the fine MSW waste. So through this screening process we have segregated the waste into different size, like 45, 26 mostly consist of plastic, fabrics and glass, and 8 to 4 mostly aggregate with fibers, and below 4.75 we found the material is more or less soil-like. So then this means 4.75 finer particles from the sieve analysis, means segregation process, we consider for parametric study, and that is chemical and geotechnical characterization for possible application future, means application in construction field. So next what we did, first we study the source material, that is 4.7 fine soil like, and what is its chemical characterization, then geotechnical and also dynamic study we have performed. Then after that we thought of whatever the rejected sample, means Kastada plant they are wasting, we thought of utilizing that waste as a fiber to improve the strength of this soil like material. So then we have collected the waste, means from the Kastada plant 4 rejected sample, and by segregating only we have taken the fiber parts, and by varying the fiber content from 0.5 to 10%, we have tried to find the optimum fiber means quantity for better strength of the composite material. So two cases we have considered. One is only you collect the waste from a dump site and segregate it, means screening process, then collect the soil like portion, and whether that soil like portion can be utilized for geotechnical application or not. For that, go for chemical and geotechnical characterization. Next is, if you are not getting enough strength here, we need to improve its strength for our application. So means like embankment or means filling or road application, we need to improve its strength. So what we can do, we can go for reinforcement. So here we are not using any geosynthetic reinforcement, we are using another waste. Another waste means this is also part of MSW only. So whatever the fibers or fibrous material present in this MSW used in Kasada plant, this is also close to our IIT-BHU. So that we have collected and used as a reinforcement to this source soil like material, and we try to give a optimum composition of this fiber. Then next is objective. So in our study, we have focused on only to check the chemical and geotechnical feasibility of MSW fines, that is the soil like material, and its application as a geotechnical construction. Further, static strength has been improved using this waste reinforced with waste fiber. I can say waste reinforced with waste fiber. Why? Because MSW fine is also part of waste, and the fibers also part of the same MSW waste. So then also we try to study this dynamic behavior, but the dynamic performance is found to be low as compared to static, and limitation of this dynamic characterization I will address. So research outline, these are the 4 steps, like first step geotechnical and chemical, of the MSW fines, then dynamic characterization of the same MSW fine, then strength behavior of reinforced MSW fine. Reinforced means this MSW fines reinforced with waste fibers. Then dynamic characterization of this reinforced MSW fines. So we got better strength here, but not here. Why? I will show you. So this shows the sample collection or site location. Site 1, Ramana site, where we have only collected the raw MSW site sample. So this site is nearly 5 to 6 kilometers from our campus, and my students, they went there and collected the sample in bags, and then kept it for air drying. So this shows the cycles of collection and segregation process. So first step, site location, collection, and air drying, and rooftop they try to dry the raw MSW. Then segregation. Segregation means we have used sieves, different sieve size, to segregate the material. And then below 4.5, this picture you can see this material is look like soil, so we consider this as soil like material, and we have considered this material for further investigation of chemical and geotechnical characterization for possible application in embankment and like filling material. So this is the outcome of chemical characterization of MSW fines only. If you see, the pH value is nearly 6.4, so slightly acidic in nature. Organic content is 5.9. So the permissible limit for organic content, it varies from country to country. So this is slightly higher side. Means we need to go for pre-treatment before application. And dissolved solid 0.81809% low, but the color, if you see the color unit, it is light yellow, so which is objectionable, so we need to reduce this. So for that also there are recommended treatment. I will show you in the last slide. So chloride sulfate content is also within the permissible limit for this particular MSW fines, means from Varanasi dump site only. One more thing I will say, this chemical characterization and this geotechnical or all the elemental analysis, it will change from site to site, because the waste and the quality of waste, it completely depends on the source. Then suppose Varanasi, then Kanpur, if you go to Bhubaneswar also, you will get completely different chemical characterization of this waste, and particularly MSW finds soil-like material. So and that's why this study is site specific, and the outcome, it can be utilized only in Varanasi area, not other locations. So this figure shows the elemental analysis result of this index energy dispersive X-ray results. Here you can see the elements present in this MSW fine soil-like material. So oxygen, carbon, titanium, potassium, calcium, and silicon also present here. If you see, few heavy metals like iron and titanium is also present. So we need to consider this factor as one of our limitation, and we have to go for pre-treatment or proper treatment is required before field application, because this may these heavy metals may pollute groundwater. And then this is the right side one, is shows the XRD graph, and here you can see the compounds like mineral quartz, aluminum oxide, potassium oxide, hematite are present. And here this one shows the concentration of compounds present in MSW fines. So if you see, nearly 49% of percent is this fourth one, silica content, followed by alumina. Alumina is this one 12.2, and then this ninth one is your calcium oxide. So this has been obtained from XRF results, and this test was conducted in CSL lab Bhubaneswar, because we don't have this facility here. IIT-BHU, they have XRF facility. So this shows the surface morphology or SEM image, same image of this MSW fines only. But for SEM means test, they normally ask for below 75 micron sample. So for this 4.75 passing sample, again we have sieved it through 75 micron, and very fine sample we have given for this same SEM analysis. So here you can see irregular shape and non-uniformity in the shape of the particles. So this is because of heterogeneity and different types of material are present, papers, and like even we find glass, and this also completely depends on the waste type. And this only we have done this much chemical analysis test, but I will add one more thing. We have not performed leachate analysis here, which is mandatory, because municipal solid waste means we are dumping the waste in dump site like 10 years, 15 years, and 20 years also. So whether it is means it has influence on water table or not, we need to check that. So that part has not been addressed in this particular study. One more student is working on it. Then coming to geotechnical calculation of this MSW fines. So we have followed all the Indian standard code for this calculation. So from the sieve analysis, the material is found to be silty sand in nature and non-plastic. Then specific gravity is slightly lower than the specific gravity of soil, 2.32. And MDD, maximum dye density, 1.51. It is also means related to your sandy, silty sand, or close to that, and OMC 18. Consolidation test also we have performed for this raw MSW sample. Compression index 0.25 to 0.12. This change in compression index is, we have also varied the density, relative density, that is 95 to 100% we have varied. So if we are changing the density of the material, means relative density, how the compression index will change, this has also been focused here. Then shear strength, it has been performed using both UCS and triaxial. UCS value 83 to 99.9 for 95 to 99% of MDD. And from triaxial test, I will show you the variation of C5 in coming slide. Then permeability, the range is like 10 to the power minus 7 to 3.45 into 10 to the power minus 7 to 1.17 from 95 to 99% MDD, which is coming within the range of low to medium permeable material. CBR test also we have performed both soaked and unsoaked. I will show you the result. This shows the grain size distribution curve for field MSW sample. This one is the field raw sample, and this is the segregated finer than 4.75 micron soil-like material sample. So this one we are using for possible application, field application. Then this first one is the compaction curve. Here you can see MDD UMC, and the middle one is the CVR results. So if you see, the unsoaked CVR is quite high as compared to the soaked one. Soaked one we have repeated 2-3 times, but we got this result only. But if you compare the CVR value, means unsoaked, okay, we are getting more than 14%, means, but soaked one, it is even for 95 it is more than 10, which is means above the means requirement of as per our IRC guideline. So for subgrade it should be more than 10, and for embankment field 5% minimum, means this severe value. Then this one shows the permeability variation with relative compaction. So with the increase in relative compaction, the permeability is decreasing. This is also obvious. So if you increase the relative compaction, means the void space will reduce. So then these three graphs is related to our consolidation results. So compression index, it decreases with the increase in relative compaction. But for CV, coefficient of consolidation, it shows the random trend. And this is the void ratio versus vertical stress variation for different relative compaction trends, 95 to 99. And this shows the shear strength improvement with change in relative density, 95 to 99. Here you can see with the increase in RC, the shear strength is increasing, and the strength parameter, particularly C and phi. So if you see here, the C value is nearly 32 to 42, means it is varying, and for friction angle 27 to 31, close to 30.75, so 31 we can say. So this is only for the source MSW fine material without any improvement, without any reinforcement. So triaxial result and even usage value also nearly 85 to 99 we are getting. So we can say, and also this one severe value, if we are recommending for embankment fill, we have to check the IRC guideline and severe and strength parameters. This source material only, it is satisfying the requirement of our embankment fill and subgrade material. So from means static test results. Then means conclusion from chemical and geotechnical analysis, what we can say here from this limited experimental study, what we found, nearly 60% of the waste material are non-plastic and silty sand, and with medium compressible and low to medium permeable material, and it is giving us good shear strength properties, you can see here. And the specific gravity is quite low, means as compared to the soil 2.32, and which made it suitable for lightweight fill material also. However, if you check the chemical characterization results, few heavy metals like iron and titanium are present. So, and organic content also little bit high. Color of the lechet also it may or it could create serious problem if it percolate the groundwater. Hence, means we should recommend some proper treatment of this MSW, particularly this Varanasi MSW fines before field implementation. But strength point of view means for our means geotechnical requirement and whatever IRC guideline they have mentioned, it is satisfying. Even settlement criteria also I will show you, that also it is fulfilling. Only MSW fines without any reinforcement. Then for the source material, we have also conducted dynamic actation. Why dynamic actation? Because if suppose this material in UP, few regions are in zone 3 and few locations are in zone 4. So if you are utilizing this MSW waste from Varanasi in the construction of any project in zone 4, so we have to go for means dynamic response analysis or seismic stability check. So for seismic stability check, we need dynamic properties in addition to static properties. So static properties, we are getting good strength parameters. That's why we thought of checking the dynamic strength parameter, particularly shear modulus and damping ratio. So this is the cyclic triaxial setup available in our lab. So Parul has used this one to perform the cyclic triaxial test of the raw MSW sample, that is MSW fines finer than 4.75, and also we have tested one for raw one. Then after means reinforcement, I will show you. So from this MSW fines test here, and this particularly G and D, shear modulus and damping ratio, we have calculated by using this hysteresis loop obtained from this triaxial test. So here we are applying this cyclic load in axial direction. So this is the sample triaxial cell. This is the frame. We have semi-automated setup available with us. So we are applying this cyclic load in axial direction by using this actuator. Then from that, we will get derivative stress versus axial strain curve, compression and tension cycle. So this is the hysteresis loop, and this one we have used for calculating the G and D using the Young's modulus relation. Then the parameters considered in dynamic analysis is relative compaction. We have varied from 90 to 98. Effective confining pressure 50 to 100, 50, 70 and 100. Strain amplitude, because we have conducted strain control cyclic triaxial test. So 0.4 to 1 mm we have varied. Loading frequency, 3 frequency we had considered 0.3, 0.5 and 1. This shows the typical triaxial test results. Like this is the input we are applying. So 1 mm compression, 1 mm tension. So here this shows till 60 cycles. So this is the axial strain variation with number of cycles. Then with this strain loading, cyclic strain loading, this is the derivative stress versus number of cycles. So how the derivative stress is decreasing with increasing number of cycle. Then this one is showing you excess pore pressure with this third one, C figure, showing excess pore pressure variation with number of cycles. So with the increasing number of cycle, the pore water pressure is increasing. One more thing I will address here, we have performed only consolidated drain test. So sorry, undrained test, U test we have performed, not CD. So as we have performed consolidated undrained test, so we are not allowing drainage during the shearing stage. That's why there is pore water pressure will be built up, and this shows the increase in pore pressure. So further we have utilized this for liquefaction analysis. Here I am not addressing that part. So this is the typical hysteresis loop or derivative stress versus axial strain curve for 90% RC and 100 kPa confining pressure, amplitude of this shear strain amplitude of 1.5, frequency of 1 Hz. Then this shows the dynamic shear modulus and damping ratio variation with first A and B figure shows the G and D variation with number of cycles. Here you can see both G and D is decreasing with increasing number of cycles. So, and the G value is, if you consider a particular cycle, so the G value is decreasing with decrease in your RC, and this third figure, C figure, it shows the improvement in dynamic shear modulus G with increase in RC. Here you can see with the increase in relative compaction, so the density of the material is increasing, so the strength, dynamic strength also is improving, similar to our static results, triaxial test result also we have observed similar response. Shear strength was improved with the increase in relative compaction. But if you check the damping ratio, here we are not getting any proper trend for damping. This test also repeated many times, but I suggested her, whatever you are getting, you report that and address the heterogeneity and complex nature of the material, because this material is look like soil but not soil. This is part of the MSW waste, so the behavior will not match completely with the soil. Then this figure left, first A figure shows the variation of dynamic shear modulus with number of cycle for different confining pressure, that is 50, 70 and 100. So here you can see for 100 we are getting higher G value as compared to 50 and 70, and this shows the damping ratio. Similarly, C figure shows the effect of confining pressure on this dynamic shear modulus. If you can see here, with the increase in confining pressure, the dynamic shear modulus also it is increasing. So this is because you are applying more confined pressure, so it will offer some additional resistance, so that is reflecting in the improvement in your dynamic shear modulus value. But for damping ratio, we are not getting any proper trend, few cases increasing, few cases decreasing. But if you check the frequency effect, here you can see the frequency of loading is not affecting much, or we can see any significant effect of frequency on G and D for this means dynamic shear modulus and damping ratio for this particular MSW fines. And this has been compared with other past researcher also. They also found effect of frequency is neglected and not significant as compared to confining pressure and relative compaction. This shows the effect of this shear strain amplitude. Here you can see with the increase in shear strain, means cyclic strain, the dynamic shear modulus is also is decreasing. And for all the cases, means varying relative compaction, confining pressure and frequency. And damping ratio, here also we are getting decreasing trend, but not means systematic random trend we are getting. So this slide shows the effect of different parameters and dynamic properties of MSW fines, fine fractions and sand, means soil also we have compared. So if you consider the MSW, so the most influencing factor, you can say confining pressure and relative density or unit weight, both for low strain modulus and this one means dynamic shear modulus. Damping ratio also only this one confining pressure and this composition, and frequency effect has been ignored both for sand and MSW. Also, our Indian researcher, they also have addressed the same. Effect of frequency is not significant in case of dynamic calculation. So conclusion from this dynamic calculation of only MSW fines is means here out of the 4 parameters we have included, from this the dynamic shear modulus of considered MSW waste is highly sensitive only towards the confining pressure and relative compaction, and which is also true for non-cohesive soil, that is silty sand. And with the increase in strain, both GD is decreasing, keeping all other parameter constant. And the trend of damping ratio versus strain is found to be random. This is means it can be justified because of the heterogeneity and physicochemical characteristics and morphology of this like irregular and non-uniform shape of the MSW fine fraction. I would say this heterogeneity of the material and this chemical characterization is affecting or it will influence this damping parameter also, and also the strain range. Here we have considered only the high strain. So maybe for low strain range, means we don't have the setup here, otherwise you could have tested. So low strain range, maybe this damping ratio means response, it may match the behavior of the soil, but for high strain it is not matching the behavior of the soil, and the frequency effect has insignificant in case of means dynamic shear modulus. This is till this only MSW fines we have focused. So from the static and dynamic calculation, static strength is means like satisfying the requirement of IFC for fill material, subgrade material, and embankment fill. Dynamic strength improvement we are getting for G, but for damping ratio, random trend. So for this, further investigation is I think required. And then what we thought of, if even though we are getting means MSW fine, the strength parameters like friction angle 26, 27 to 31, if we can improve it further, it can also be used for like foundation material or other applications like backfill material, means so that bulk quantity of waste can be utilized. Then I have 10 minutes time. Then we thought of improving the strength of this MSW fines by reinforcing it with waste, another waste, that is the fibers, part of the collected waste only. So this shows the induced fiber, means collected from Karsada plant. So this is the Karsada plant in Varanasi, waste to energy plant. So they are generating power from this MSW waste. So the second site, and here we have collected 4 mm rejected sample from the site, and then we have followed the segregation process. This is the raw rejected sample collected from this Karsada plant, and we followed the air blowing approach for segregation in our lab. Then this is the fibrous material we have considered for improving the MSW fines strength. Then we have varied this fiber percentage from here. You can see mostly we can see threads, cottons, and like dried. Mostly maximum percentage is like cotton and threads. So here no soil-like material we had considered in the fiber. So this fiber content we have varied from 0.5 to 10%, and then we have done the compaction test, how the density is changing. So with the replacement of these fibers and this MSW fines, the MDD reduces and decreases, and also this OMC is increasing. This is because if you see the fibers here, it will absorb water because of this composition of the fiber. So next please. This is the compaction results by varying the fiber content. Next, this one is showing you the means like sigma D versus axial strain obtained from static triaxial test. So for different fiber content, 0 means source MSW fine only, what we have done in the previous means case 1, and then here case 2, 0.5 to 10% we are varied. So with the increase in fiber content, we are getting improvement in the sigma D value. And here right side table you can see both strain parameter, friction angle, and C value. So 2 cases here also, 2 cases we have considered for the triaxial by keeping density as fixed 1.59 whatever the density of source MSW fines, then by varying the density from this figure, because for different fiber content we will have different compaction curve. So suppose this one 10%. So for 10% the density MDD is nearly 1.35 or so. So we have considered the tested perform this triaxial test considering both the density, like varying density from this different fiber content and constant fixed density, like density of MSW fines 0%. Then replace the soil with fibers, like replace in terms of percentage of fibers 0.5, 1, 2, 5, 1, 2, 4, 8, and 10. So if you see both C and cohesion and friction angle value are increasing with the increase in fiber content. And if you check this friction angle value of 8 to 10%, there is not much difference in your friction angle between 8 and 10%. So considering that, we have considered this 8% as optimum fiber. Then conclusion from this fiber reinforced waste study, particularly only static study. So addition of waste fiber, that is 8% by weight in the same MSW fines, it shows remarkable improvement in the static strength characterization of MSW fines, even at a higher strength. If you see the 20% strain, till 20% we have tested, then the considered material after reinforcement can be suggested as embankment or subgrade material, subgrade fill material. With reinforcement, we will get better performance. With reinforcement means with this fiber, waste fiber reinforcement. Without fiber also, that is satisfying the requirement of embankment and subgrade fill material as per IRC guideline. Then for this fiber reinforced part, we have tried to explore the dynamic strength parameter also. So here this optimum fiber we have considered, but limited test we have performed. So unconsolidated under UU and consolidated drain test we have performed. So for different fiber content, axial strain we consider 1, and each one test we have performed. For UU test, CU we have varied the fiber content 0.5 to 10, but the axial strain only 3 we have tested, and we have considered the density as constant of MSW fines 1.51, frequency 1 Hz, confining pressure 100 kP. So from this, if you see the dynamic shear modulus with number of cycle curve, here there is not much change in the dynamic shear modulus value, and for different FC and UU test, particularly unconsolidated undrained. But if you see the CU test, first figure, A figure is UU result, B, C, D for CU result. So for CU case, we are getting decrease in G value with increase in number of cycle, but for UU we are not getting that. This is because the sample is not even saturated, it is only in compacted sample, and we have applied the dynamic loading. And this shows the damping ratio curve, damping ratio variation with number of cycle for the different reinforcement case. And this is the summary of our second part dynamic test results: dynamic shear modulus and damping ratio variation with fiber concentration from 0 to 10%. If you see here, with the increase in fiber content, we are getting improvement in strength in static case, but not in dynamic case. So shear modulus is decreasing and damping ratio is increasing. Here also random trend you can see. So means both for UU and CU case. This is because means even after the testing we tried this test, we have repeated many times. So what happened after mixing this fiber to this MSW fines, so we are able to make the sample, but we can see the fibers like threads, and so it can take compression, but in the expansion tension cycle, this means the interaction, or you can say interlocking, is lacking in case this dynamic test, and particularly dynamic loading case. So I would say under seismic scenario, this fiber reinforced is has limited scope, and but only MSW fine, it has proper cohesion and friction and angular friction and cohesion value, so that can be used in low seismic risk region. But with this particularly waste fiber, it is not giving us means improvement in dynamic parameters. So conclusion from this fiber reinforced waste is no improvement in dynamic shear modulus of this MSW fine with fiber content has been noticed. And if you compare, there is relatively low rate of degradation of percentage. 8 to, if you compare 8% and 10%, rate of reduction is low, but still it is decreasing, you can say. And the dynamic study on reinforced MSW fine doesn't show any improvement in dynamic strength parameters and the cyclic strength, hence limit this particular study. Then what, so this part is our failure, I can say, reinforcement, but still I recommend her, whatever you are getting, you have tried, you put it in the thesis and address the problem. It means like fiber waste, it is not reinforcement, it is not giving better strength under dynamic case, but static case we are getting improvement nearly 39 to 40%. So then we try to recommend this material for embankment fill. So this embankment means there is a proposal that 4-wheel lane near the same Ramana site they are going to have. So for that particular plan, project, in our lab we got the sample for testing. So then I thought of if the same site we are also doing for research part, and for this 4-lane road we are also we are having same testing thing. So let us try to design this 4-lane road and check our suitability of the material. So what we did numerically, we have used Plaxis 2D software for the analysis of this embankment. Particularly, we have considered 5-meter height with 0.5 meter soil cover. Top width for this 4-lane road 16 meter we have considered, and side slope of 2:1. And traffic loading, because this is a village area, so 10 kilonewton per meter square we have considered. And water table 13 meter. This is this has been taken from past report from that particular Ramana site. Then these are the parameters we have considered for analysis. This shows the contour fill of your vertical or total displacement. Here you can see nearly 55.6 mm of total settlement, and this shows the vertical settlement at different sections. Here if you see section 1 is the left side one, this is the section 2-2, section 3-3 mid slope, and section 4 end slope. So at different location, how the displacement is varying, B figure is showing. This one shows the total stress variation, contour fill, and with depth variation at different location. This is the horizontal stress variation, and this is the shear stress variation with depth. And in addition to that numerical part, we also have calculated the settlement analytically. So using this consolidation equation, settlement, primary consolidation settlement, and here we are getting nearly 70.9 mm of settlement, total primary only primary consolidation settlement we have obtained. And from the analysis, if you check here, nearly 55.69 or 56 mm of settlement. So both the settlement, numerical analysis and analytical results, this is within the allowable settlement range, that is 300 to 600 mm as per IRC 75 for low design of low embankments. So this, but I would say this material is suitable for embankments, particularly low embankments. And the site is also Ramana site is also in village zone 3, Zone 3, and low volume traffic it can be predicted. Then concluding remarks from our studies, particularly we have focused how to reutilize or reuse this waste portion of MSW fines or reinforced MSW fines. So, and the sample can be suggested to use in low seismic risk region. Low because under dynamic condition it is not giving us improvement maintain strength parameters, but under static loading condition, it is giving means good strength parameters and satisfying the codal provision. Only another thing is the chemical characterization and the presence of heavy metals. So proper treatment so we have to recommend, and that also depends on the percentage of this heavy metals contribution in particular material. So like treatments, thermal, biological, base separation, even washing also we can go for. Blending with local soil stabilization, we can mix it and check whether the heavy metal percentage is decreasing or not, or whether it is within the limit or not. So this chemical characterization and chemical pre-treatment is required, but strength and technical guideline, all other codal provision, it is satisfying. This material, particularly MSW Fines, is satisfying for embankment fill material. Then utilization of this soil-like waste, first step is we need to screen and segregate it properly. Then you have to take the MSW Fines, go for treatment depending on the presence of heavy metals. If you have, then potential use, you can use as soil means cover or compost, cover material, then recovery of rare earth element, then geo material or fill material, construction material. So our study is focusing on this last two, fill material and construction material, how to potentially use. These are the few proposed utilization scheme for MSW Fines in past studies. So if you see in US, mostly they are using this MSW Fines, particularly means soil-like material. They are using as cover material, and a few country they are using for energy generation, like in Varanasi also we have one. And here, if you check these are few more. And if you check our Indian scenario, in Gazipur, East Delhi, they have used this MSW Fines for embankment fill material that is height of 3 meter to 5 meter, 5 meter embankment fill. And this Ramana side, from our study also, we have recommended for this their future upcoming this four-way, this 4-lane road project. Then if you check the recent project of NHI, National Highway Authority of India, so this they have asked the Municipal Corporation of Delhi to provide nearly 365,000 tons of inert material, particularly MSW fine material, for the urban extension road 2 project. So this much quantity of MSW Fines is going to be utilized for this extension road, and which is the 3rd ring road of this capital. So this is, I think, all about our case study results, and these are references. So thank you all. Lastly, I will say, so this is the only one space or one home we have. So we have to preserve it and save it for our own only, because we have to live here only. So it is our we are only generating the waste, and it is our responsibility to utilize it in the proper way and make our environment sustainable. So thank you all, and I will be happy to answer a few queries. Yes, because if you check the past or Indian scenario, the MSW pH value, mostly it is alkaline in nature, but our Varanasi site, it is slightly acidic in nature. So it will affect the groundwater quality. So that's why we need to reduce it. So the recommended treatment is washing we can go for, or mixing with soil. It will reduce the pH content. Particularly for Varanasi site, we have titanium and iron, but the percentage is low. Still, we have to go for chemical treatment. No, actually, this treatment process is not tedious, but we have to go for pre-treatment before using it for suppose embankment. Pre-treatment means even we can go for lining. So that our objective is, if heavy metals are present, it should not pollute the water table, groundwater. Suppose embankment, so you can go for a lining. Yes or no? You can provide lining material. Then you can use this as embankment. Fill material. treatment thing, optimum treatment approach technique we need to suggest based on the requirement, whether heavy metal percentage is within the permissible limit or it is exceeding. If it is exceeding, what will be the best treatment technique for that particular waste? So the treatment, there are different treatment, means we can go for soil mixing, washing, and chemical treatment also, but it depends the waste type and the type of hazardous material present. So depending on the hazardous material present, we can, means you can recommend the test. This also need detailed investigation, because MSW people have not yet accepted it like fly ash. So more detailed study is required. I think in within 10 years or so, people will accept slowly in because huge quantity of waste can be utilized in this embankment or highway project. So you know how the highway construction and our means transportation sector is expanding in India. So there only we can utilize even our means quality waste, we can say. Yes, whatever the
It's
result I have shown you, means every results has been checked as per the IRC guideline. I have mentioned 75, IRC 75. So all the test results, first step is if I am focusing on embankment, so I have to check the MORTH and IRC guidelines. So that total provision we are checking, and this is the first step. You have to focus the means application part, in which area we are going to apply and what are the standard, particularly Indian scenario. We have to consider that, and it has to satisfy the first, similar to our building design. So IS means IS code provision we used to means follow. Here also embankment means embankment, this waste we are utilizing as embankment material. So for embankment design, whatever the Indian standard and IRC guideline more, that all the codal provision we have to follow, and particularly this Varanasi waste MSW fines, it is satisfying it, both settlement point of views and severe and strength. Thing is only chemical, this heavy metal, presence of heavy metals. So for that, further treatment is required. Otherwise, strength wise, it is fine. Only chemical and this heavy metals.